you. Thank you, Gordon. Thank you, Mike. So we can we can start the discussion, perhaps focusing on the interaction between the processes that have been illustrated by Gordon and Mike and society or environment-related questions. For instance, Mike, I had a question on these magnetic phases that you were talking about. Do you think that changing the process, that means being less reducing, could give TiO2 particles instead of this reduced form of magnetic phases?
Yes, if you change the conditions in the firebox of a coal burning power plant and made it more oxidizing, and you can do that. It's expensive, but you can do that. It would reduce the production of magnetic phases. Yes, absolutely.
Are you optimistic? Excuse me. Are you optimistic in transmitting this message to industry or to politics?
Yeah, and so I'm glad you mentioned politics, because when we published the first Nature Communications paper, we not only made the homepage of the Department of Energy, but we also made the homepage of what's it called? CrazyScience.com or something like that. It's an alt-right site, and they said, this is ridiculous, it can't be right, you guys are crazy. And so we made their homepage. That was really, I was very proud to be called crazy. So yeah, so we are, the Department of Energy is really, knows about this now, and we're working with them obviously, and yeah, so it's well known.
Okay. So first, yes, Alex, if you want to ask.
Yeah, good point, Alex. It is more complicated.
So, yes?
Mike, you show, obviously that paper is specific to the health effects of those phases in the lungs. This group of people here spent a lot of time looking at medical literature in terms of
Quite a lot in the medical literature, but as you know, John, when you look at what the doctors and the biomedical researchers are working with, they usually don't even know their mineralogy at all, and so they usually even have misidentified the phases that they're trying to study. So that's why a lot of you, and I've been involved, Gordon's been involved in this too, we work with the medical people directly. And then we get the studies right. You know, obviously they know best on certain things, we know best on other things. And so it's a collaboration that works well. And I should mention, and we should get Gordon involved in the discussion too, but I'll mention one more thing. Because nanomaterials are so difficult to control, and in this case they're all over the planet, but whatever mine in any kind of mining operation, as I showed you earlier in my talk, you're going to be making massive amounts of these things. They're so difficult to control that for mine sustainability, what you have to do is not, as Gordon showed, you don't want to bring rocks out of the ground, process them, and then dump them somewhere on the surface. They have to go immediately back down into the reducing zone. And so when you looked at the Mike Horse mine, they moved, in that tiny mine, they moved 1 million cubic yards of slag. And where are they putting it? They're putting it back underground. Well, if they would have done that in the first place, we would have never had that problem. We wouldn't have the Clark Fork Superfund site, the largest in the United States. They wouldn't exist. So that's the most important message I can leave the mining industry, and I've talked with Larry and Murray about this, Gordon, is that whether the mining is underground or not, you're bringing a lot of stuff to the surface, and that stuff's got to go right back into the ground. When you're done with it, put it away.
Yeah. Yes, please.
I don't know if you've all seen the Stanford out and the critical minerals
Yes.
put out about a year ago. Arsenic and titanium
that? There it is right there.
Yeah.
No, I mean,
No,
I couldn't
no,
agree with
structural
you more,
resources.
and there is that waste to wealth that is moving. It's also a social movement now, and it's absolutely correct. It's got to happen. Now, the reason that it doesn't happen as quickly as it should, and everything else, like what I just suggested, doesn't happen, is because it's expensive. And so instead of copper being X cents per pound, it's going to be 3 times X, or 4 times, or 5 times. But we have to learn to pay forward on these things. We can't pay in arrears.
Evolution, yeah. Yes, and also perhaps changing from pyrometallurgy to hydrometallurgy. In that case, you can have various ways of extracting more elements from the same ore. That means instead of exploiting for one metal and the rest is put away as a waste. And a waste is more and more a secondary, primary resource.
A question for both Gordon and Mike. As we think about minerals, particularly in the realm of health effects and environmental impacts, what do you guys think, or what does anybody think, about what we need in terms of analytical advances and approaches to define fundamental crystallography and chemistry towards reactivity that would be important in defining those things?
One way that we could improve things in terms of analytical techniques is to have brighter sources of photons, so we can look at smaller amounts of elements in different materials and smaller materials themselves, the nanomaterials. And this thing I mentioned, the LINAC coherent light source at SLAC at Stanford, is one of those ways of doing that. It will increase the brightness relative to existing synchrotron sources about 16 orders of magnitude. So, yes? Chris, I don't know about defects. That's a different type of measurement. I'm just talking about elemental detection or small particle detection. With these much brighter beams, you can focus down. In fact, they come very focused anyway, and look at individual nanoparticles now. In fact, you can do what's called X-ray microscopy using synchrotron light sources to study individual nanoparticles. And right now, the lower limit is about 10 nanometers in terms of resolution. So we're getting there. I'm sure there'll be other. In fact, another technique that's not so new, but it's really becoming extremely popular is CryoTEM. And there we have the ability to actually solve crystal structures with resolutions that rival or in some cases exceed X-ray diffraction studies, specifically for proteins that are so difficult to determine structures of. In fact, there will be more Nobel Prizes awarded for more discoveries of structure property relationships in biological molecules in the near future, I think, because of the cryo-TEM methods that are being developed right now. So that's another new method that I think has lots of promise for mineralogy.
But Gordon, this raises also the question of what is a mineral. That means decreasing the cycle down and down. We are totally out of the classical definitions of minerals.
That's right. In fact, I think I'm looking at Gabriella over there. We need a new exhibit at the Smithsonian on nanomaterials, but the problem is how do you show them to the public? They're so small. So we should actually have electron microscopes in the Smithsonian as sort of an exhibit where people sit down and look at the images of these nanoparticles. That would really be a neat exhibit, I think, if you could find the money for that. Vibration? Well, that's what the cryo-TEM gets. The cryo-TEM actually helps that a lot because it damps things down to the point. We're down, very low in temperature, so the vibrational motions are really damped at that point, and you can see things that you can't see otherwise. let's let Mike handle that here.
They're exactly right. And electron microscope companies have put a lot of money into vibration isolation, and they can do it now. So even with machine shops nearby. But the problem, good point, you made a good point, because the problem is to retrofit your particular room to be able to do atomic resolution TEM would cost about $300,000 just to modify the room. Not to mention the $5 million it takes to buy the microscope.
A very simplistic question to Gordon. When I'm painting gold, when I'm painting gold in Hell's Canyon, and in the gold pan there's a big drop of mercury, do I know whether that came from Cinnabar, which is a town in Idaho, right on the river, or was used in gold mining? Is there a way to tell?
I don't know that you can connect it directly to gold mining, but here's the example I talked about was the California gold country, the foothills of the Sierra Nevada. So far as I know, there's not a single mercury mine up there. The only mercury that was up there was transported by humans to use for amalgamating the fine-grained gold. But what we found is that it's not, I mean, I'm sure liquid mercury is coming down from the mountains into the Bay Area, but a lot of the stuff that's coming down is nanoparticulate cinnabar. And so somehow the liquid mercury has been transformed, probably in local reducing environments, into cinnabar, mercuric sulfide. And that's what's being transported by water down to the Bay Area. So again, that's a good example of an indirect incidental nanoparticle. We didn't intend for that to happen, but it did. And those tiny particles, by the way, it turns out are much easier to methylate by bacteria than we thought. But to connect it directly to actually say this liquid mercury is connected to gold, I'm not sure how you do that.
I'm sorry, I got to say one more thing, and this will come up in the next segment too. What he's talking about, and what I'll just say now, is that just because it's nano, it's not just it's small. The properties of your favorite mineral, when you make it really small, completely change. Take gold, for example. You make 5 nanometer gold, it melts around 427 degrees, when bulk gold melts at 1,069 degrees or something like that. Gold, when it gets small, it's not an inert material anymore. It's highly catalytic, highly catalytic. It's not even gold anymore. It's pink or red, and on and on and on like that. So the whole world of mineralogy completely changes in the nano world. And in Jeff's exhibit, right, Jeff? You're going to do a nano exhibit at the Smithsonian now. He's not only going to have pictures of all these things, but he's going to have the complete different list of properties that every mineral is going to have to go through. And that's why there aren't 5,400 minerals. There are probably 20,000 or 50,000 because the properties completely change. They even gold goes from a conductor to a semiconductor. It's completely different.
Gordon, there's lots of different stable isotopes of mercury. I was wondering if anybody's used the isotopic chemistry to any use.
Yes, in fact, we tried that at the New Adria site. Ruben Kretschmar came over and spent a sabbatical with me for a year about 5 or 6 years ago. We published 3 papers looking at the stable isotopes of mercury. It turns out that, I remember years ago I gave a talk at Yale University when Carl Tarikian was still alive. And we just started doing mercury at that point and looking at isotopes, and he said, this is a complete waste of time. The mass is too great. It's not going to be affected by biological processes, and the bugs just can't do that. He was wrong. It turns out that there's quite a bit of fractionation of mercury, and there's 7 stable isotopes, by the way, that you can look at, and that's now being pursued. In fact, Joel Bloom at Michigan has been doing this for years now, looking at stable isotopes of mercury in things like permafrost and so forth. So that's an active field.
Okay, so we will break the first session and move to the following one, which is not too far.